Hi, everyone. Hi, Ankit. Hi, Mukesh. Looks like there's some kind of confusion that the email did not go, but great. Let's just start with you. Do you have any questions for me? Hi, Ankit. How are you? And hi, Mukesh. Are you able to hear me clearly and see the screen clearly? Oh, I need to put the headphone. Just give me a second. I'll just put the headphone. Yeah, go ahead. You were saying something. Is the voice clear or should I try again? Okay. All right. So Mukesh and Ankit, yeah, are able to see my screen and hear me clearly? All right. All right. Great. Great, Ankit. So do you have any questions with respect to the end-to-end project? Hi, Amitva. Are you able to hear me? Mukesh, Amitva, and great. Ankit is able to hear me clearly. If you have any questions, please feel free to ask. You can use the chat window to communicate. In case you have a question which needs unmuting, just let me know and I can unmute you. Okay. Wonderful, wonderful. So great to have all of you in the session. There were around 15 people who were interested in the session. So probably there is some kind of confusion or the email did not reach or something happened. Did you guys get the email about the session? But that's good. I mean, if we are just 3 people, we can spend more time. We can spend more time. Yeah, the initial email read the first June, and then there was a follow-up email, and so on. All right. All right. So yes. Great. So all right. So we can utilize this time that we have in order to. I mean, we can spend more time on Q&A, and that way it'll be quite useful. Okay. All right. All right. Good question. Thank you, Ankit. Question is that we have a video of Azure ML, right? And the doubt is that how to remember it. It seems that we need to watch every step and repeat it, and so on, right? Okay. Okay. So what I'll do is I'll basically, what I'll do is I'll give you an overview, and probably they'll give you the reasoning why we are doing a step or not, why we are doing a particular step, and so on, right? Okay. So the first thing is we need to keep in mind the checklist. Okay. All right. So one thing that we essentially do as part of the machine learning project is that our sole objective is that given the data, given the data, we want to come up with a model, right? We want to come up with the model, correct? And once we have this model ready, it'll be able to do the predictions, right? We call this predictions, or we call it inference or production environment. Okay, this is prod, and this is training. Okay, just like in case of human, there is a phase of training in life, and then once we are trained, then we can do the rest of it. Like, for example, when we were kids, we were playing and we were learning based on all the data that we were generating, and then we were building our mental model. Now, once we build the mental model, now we are able to do various things. We are able to walk around, eat, all of that based on the training we had in the childhood, right? Similarly, we do with the machines, and we first train it based on the data we have. The data is broken down into, data has, you see that data has something called example, or you can say instance, and there is the result of it. We call this label, right? And this is an instance, correct? So we basically convert our data into the the labels and the instance. And the important part to understand here is that this is, when we say something like a record or experience or observation, it essentially is built up of various features. Feature 1, feature 2, feature 3, or you can say characteristics. So the past data, we convert it into features or experiences, or you can say features, or you can say attributes or properties or characteristics, right? So let's say there's a photo, each pixel is one feature. And the label is whether the photo is a male or not male, or the photo is cat or not cat, or the photo is having the label like 0, 1, 2, 3, 4, 5. So basically that's the label, like the one that we are trying to achieve and so on. So this data has this. Now theoretically, this looks very nice, but the challenge is that when we build this model, how would we know that we have built the right model, right? We would never know that we have built the right model, and we would be happy that, okay, I'm thinking that this model is great, but how would we actually know that the model we have built is doing good? So what we do is, this data set that we are talking about, this one, okay, we break it down into two parts, okay? We call that testing and training. On the training part, we basically build the model. On the testing part, we test our final model, okay? Further, so that's something that we do. We start with the data. We first of all convert it into features and rows and columns, and then we split this into two parts. One is this, let's call it training data set, or can I just have empty? Yeah, so let's just keep it here. Okay, this is how it looks like. So we got the data, we are preparing it for the production, and we break the data into two parts. One is called training, other is called testing, correct? Now, while we were breaking this data, the chances are that we end up, with a bias set, okay? We end up with a bias set, and we basically, let's say we were predicting from the photo whether it's a male or a female, and we end up training only on the males. Therefore, this data set needs to be well stratified, okay? It should be something like from every strata, the values should be here as well as here. Rows from every strata should be both sides. So we shuffle it, and then we break it down into these two parts. Perfect. That's the starting point. So we got the training data, we got the testing data, correct? Now this test data set, test data set, we keep it like separate. We never show our model that we have a testing data. We never let model peep into the data, okay? So that's the first thing. We split it, keep it aside. Now when we have this, then we start doing the other parts, like when we have, so first is splitting the data set, first is feature preparations, so on. And then once we have the training data set, right? Once we have the training data set, what we do is, first of all, we look at the training data set itself, like how does it look? So we try all kinds of visualizations. Okay, we do the visualization, right? That's the first part. Then we do, let's say, removal of missing values. Okay, missing values. Because lots of algorithms don't like missing values. Third is in case, because at the end of it, we have to convert this data such that each column is just full of numbers. But if you have data as like categories, like good, better, best, right? Categories, my handwriting. Okay, let me just see if I can. Okay, so, okay. So when we have like categories, then we need to convert this into data set, right? That's use the hot encoding. So essentially right now we're getting ready for feeding to the algorithm, right? And once we have also, I think here, missing values, and there are a few more things. Okay. The other way to do this, okay, other way to learn it, Ankit, would be that instead of going linear, right, we try to go directly to the last step, okay? And then you observe, where did we go wrong? So the first step was creating the data frame kind of model, loading the data, then splitting the data, then splitting specifically normally what you do is you initially start with just whatever, without any of this magic, okay? Don't try to visualize, don't try to pick the missing values, and don't try to do any of the magic, let's say. Now, what you do in such cases is just try to go to the last step. Last step is, let's say, train the model, right? Last step is train the model, okay? Training, and what we do is, in the training, we want to try out multiple algorithms, right? So we do cross-validation, right? So in the cross-validation, what happens is that one algorithm, so we don't want to show the algorithm the testing data, right? So what we'll do is, it'll again split the training data into, say, 90-10, and on 90% of the records, the algorithm will be trained, and 10% it'll be tested, okay? And once that is done, what we do is we do the hyperparameter tuning, okay? Right? Hyperparameter tuning. Correct, that's right, Ankit. So 80% data is again divided into 90-10 here for every algorithm. Okay, because why are we doing this? One thing could have been extremely simple. Okay, one thing could have been, one way could have been that, let's say, we have a very simple problem. Let's say, okay, I hope till here this linear path is okay. Let's just go non-linear for a moment. Okay, let's just go non-linear for a moment. Okay, and I'm going to just clear everything, and Is there a better diagram? The page which has nothing on it? This will be even worse. I think this is the best. Perfect. Now, let's just start with a very simple thought that what we're going to do is just take the data. We load the data first of all, right? We basically load the data. Okay, that's, let's say, first step. Create the data table, right? And then second is train the model, training phase, right? I hope you are clear about this part, or you can say not train. I'll just not go with this. Okay, we will say second is split, right? So split into 80-20, and then let's say instead of going further, we do the training. Okay, training of an algorithm. And then 4 is, let's say, testing, and 5th is deployment. I'm going to, let's say, short circuit all the things that we learned, right? Testing and then deploy. Okay, so what are the challenges that we will face? So what are the challenges that we'll face here in this case? In this case, the first challenge that I can see is there are multiple challenges. I'll let you guys come up with the challenges. In this approach, what problem do you see? We load the data, split it, do the training, and then do the test. On the splitted, do the test and deploy. What are the challenges do you see? Ankit, Amitva, Mukesh, Amitava. Is it okay if I call you just Amit or all right? So great. Suggestion for Ankit is that are we testing multiple algorithms or just the one? Perfect. So first problem that we see is we should test multiple algorithms, right? Correct. Now, how would we know which of these algorithms is doing good? One way is that, let's say, we do the training on all the algorithms and then come back to testing. Now, what will happen in that case? What will happen in that case is that we did not give algorithms a chance of improvement. We basically exposed our testing data, right? So instead of that way, what we're going to do is further, we are going to break this into parts. We're going to break this into parts. Okay, we're going to say break this into further parts. Okay, this will become, let's say, we'll break it into 2 parts. One is called, let's say, cross-validation, right? Cross-validation. Okay, cross-validation, and then training. Now, I mean, training includes cross-validation. Okay, I'll just actually type instead of drawing. Okay, so we will basically do the cross-validation. Cross-validation includes the training, okay? And then we will also split it into, then once cross-validation is done, we'll pick each, the algorithm which is performing the best and do the hyperparameter tuning, right? Good, good. What else? So your first question made us do the other step. Now, what other problems do you see in this approach? Now we have got the approach like load, split, then do the cross-validation, and then do the hyperparameter tuning, and then do the testing and deploy. Okay, hyperparameter tuning is what? Hyperparameter tuning is select the best, do the cross-validation, right? The result of it will be select best algorithm, right? best model. That will be the objective of this one. And for that model, we further try all kinds of arguments. Okay, we further try all kinds of arguments, all right, all values of different knobs that algorithm is giving us. And then we basically do that. Now, we don't know what all parameters are there, what values are right, what values are wrong. So we let the system figure it out by themselves, right? So what we say is, we tell the system, hey, why don't you try 0 to 100 for this particular parameter, hyperparameter, and 0 to say minus 100 to 100 for this, and so on. And then for that particular model, the best model that you have selected, we are further making it fine-tuned, right? Perfect. Great question. Great question. And keep these questions coming, because these are the questions that are shaping up the discussion and the understanding of the subject to all of you. Yes? Any other? There was one more answer from missing data would be an issue. Thank you, Amit. So here, there is, right? So missing data could be a big issue, right? So question is, where will that be? So here, after split and between training, we will have to fill it with the missing data, right? We'll have to, here, this particular place, we will do the fill missing data, or we just put a larger one, tackle missing data. Okay, so that goes here, right? That goes here. Any other points? Yes, the other problem could be that the data is skewed or labels are skewed. In that case, while splitting, we have to modify the split and do the, you see that change the split to stratified split. Okay, we'll call it stratified. Okay, so split becomes stratified split. Good. A question from Ankit is, how do we decide what 80% goes to training and what 20% goes to testing? Good question. Generally, what we want to do is, we want to randomize all the records, okay, and then split it, because we want as much shuffling as possible, so that the algorithm or the model does not learn a particular behavior, right? Perfect. Great question. So any other problem that you see, we loaded the data, we did the stratified split, then we tackled the missing data, right? And then we did the cross-validation, and then we did the hyperparameter tuning, and then we did the testing and deployed, right? Now, this cycle that you see here has evolved. In this class, what we've done is the learnings of thousands of people, we have converted that into this process, right? Now, it's a very important discussion that's shaping up my understanding also, that probably what we'll do is, we will start with extremely simple approach, and then we will keep on fine-tuning it till the point we get the best results, okay? So if we do really, really basic things, then the testing would give us not very great accuracy. Then you go back, tackle missing data, do not drop the columns, we do other things, and so on. That way, our accuracy will keep on improving, right? Any other thing that is missing here from your understanding? Okay. One way is like nice learners. One way is that you memorize all these steps. The other way is the way we had this discussion, the way you guys questioned it. Keep that attitude that way, because in case you are memorizing, the chances are that when you are solving hard problem, you will not innovate. Also, when you're solving a hard problem, you may not be able to recall all the steps. Okay. Therefore, keeping the approach whereby having a very simple approach first and then going complicated, so that you have a hunch about the entire process. You have the reasoning why we are doing something and why we are not doing something. Right? Question from Ankit is, what basis are we selecting algorithm? There were multiple statistic ways to get the error. How do we decide which statistical tool method to use? Very good question. Very good question. So right now, the only way we are deciding is based on the accuracy. Okay. So it's a very interesting question. So when you look into this question, so there are multiple aspects to it. So I'll just take one thing at a time. Yes, good questions, good questions. So I'll basically start from there. Okay, so all right. I think I should take the second question first. The second question is, how is accuracy measured? How is accuracy measured? So how is accuracy measured is, it's a function of what problem are we trying to solve, right? What problem are we trying to solve? Based on the problem type, we choose the measure of accuracy, whether it's regression, or it is a classification, right? And in case of classification, it can be further categorized as like multi-class, or it can be classified as binary classification, or it can be classified as multi-label, and multi-class. Okay, so now this type of the problem is what decides what accuracy measure do we use. Okay, so in the classification, you have, this is the first one, this is the second one, and so on, right? This is the first one. Okay, let me just try drawing it. This is the first one. This is a case where we are saying spam / not spam, right? In which you have yes or no as the answer, correct? So that's the binary classification. Basically, if the label, the last column, the one that we are predicting, is only having yes or no or true or false, then this is a binary classification, right? Then second one is the multi-class one. What is multi-class one? Like, we are predicting whether, given a photo, I think regression, everybody's clear, right? When we are predicting a value like 1.20 and so on, yeah? So then there is multi-class, multi-label, and so on, right? That's the second exercise we are going to do. So based on this, we choose measure of accuracy, okay? So if it's binary classification, the logistic one works out. Then if it's a multi-class one, then there is a there is a softmax loss, and there is something called what do you call? There are many more ways we will discuss as we go ahead. One of them is coming up with the precision and recall mechanism. And when we have multiple label multi-class, this is hard problem. Okay, then we have the most recent one that people use is called LOLWRAP. LWRAP. Okay, so that's called LOLWRAP. Okay, so basically based on the kind of problem we are solving, these problem statements, these measures of accuracy keep on changing. Here, in case of regression, in the case of regression, we are predicting a value like 1, 1.0, 2.0, and so on. Here, generally, the accuracy measurement is done based on mean square error. Perfect. We're going to more details. Okay, so question is, I'm a bit unclear, how do we decide between regression and classification? So regression means our objective is to predict what is the outcome, as in actual value, right? Like in exam, when you go to an exam, there are multiple kind of questions, right? One kind of question is MCQ, multiple choice questions, right? And the other kind of question is fill in the blanks, right? In which you have to fill in the number. So regression is that fill in the blank, while classification is the multiple choice questions. Okay, so that's a kind of you can think of. If in the problem statement you have to predict what kind of classification it is, right? Then sorry. In the problem statement itself, you will come to know whether it's regression or classification. If it's a regression, then what to do. If it's a classification, what to do. All right? Multi-class is, you see, multi-class is like, we call it MNIST. We're going to talk about MNIST later. The handwriting recognition on the digits. And multi-label is, let's say, we record a clip. We record one clip and we ask the software to predict what are the objects or what are the sounds that you hear. So it'll say that, okay, there is one man talking, there is a fan moving, and so on. And then there's a wind blowing, those kind of multiple answers it will give. Okay, that's called the multi-label. Every instance receives multiple labels. That's called multiple labels. We will go into more details in the next chapter on this, but it's very important to understand this one. Okay. So that was the first question that we were trying to answer. The question is that how do we figure out which algorithm to use? When we say, do the cross-validation select best model, on what basis? On the basis of the error, right? On the basis of the minimum error, which of the algorithm, let's say we are trying, say 10 different algorithms. Let's say we consider every algorithm that we don't know what it is, right? So we say, okay, we tried, say, decision tree, though even if we don't know what is decision tree, we tried, say, random forest, we tried, say, neural network, and we tried, say, any other suggestions? We try, say, SVM. Okay, so based on the type of the problem, we will basically specify the model accordingly, whether we are going to use decision tree regressor or decision tree classifier, right? Similarly, random forest regressor or classifier based on the problem statement. And then what we're going to do is we're going to observe the error, pick the model which is performing the best. Okay, that gives us the best answer, and then we move ahead. Right? So cross-validation is nothing but, let's say there were let's say, imagine that this is our number of rows, okay? What we do is, for first model, this is 80% of records, okay? This is 80% of record total from here to here. Okay, this is 80%. We further make it like, say, 90% and 10%. Okay, so we train the model on this part, test it on this, then we basically change this to, say, here, this portion, and for remaining part, we train it and test it. And then compare, like compute the average accuracy that we got, and that's what we call it, cross-validation. So there will be how many such sets? First, this one is testing, then this portion will be testing, then this portion will be testing, this portion will be testing, and so on. There will be total 10 such cases, correct? All right, so wonderful questions. I hope I was able to answer your question, Ankit. Okay, a very good question. Thank you, Mukesh. Question is, we talked about the accuracy as the prime criteria of selection of the algorithm. Is there any other criteria? Good question. So there are some more criterias and the ground rule. In case your problem statement says that, hey, can you also, we don't want only the accuracy, okay? We want the reasoning behind the accuracy. It's okay to come with a model which is performing bad or which is not performing the best. We want okayish accuracy, but we want interpretable results, right? Let's say we have our sales data, okay? And you get a target saying that, hey, here is our sales data. Can you come up with the parameters which are the most important or crucial with respect to our outcome? Okay, so what you do is you utilize the simplistic models, such as, say, normal linear regression models, or you utilize the decision tree, because using these models, we can clearly say that these factors are most important, these factors are less important. But if you are using, let's say, a far more complex model, such as say neural networks, it'll be very hard to say that which parameter is impacting the outcome the most. Okay, which parameter we are impacting, which parameter is impacting the outcome the most. Yeah. So generally, based on the problem, what we do is we look at the problem statement closely. And this is a very interesting interview question, and thank you all for asking these questions, because these questions are what people ask in interviews, most of these questions, okay? So this is a very, it actually happened, one of my learners came to my office, and he showed the problem statement that, hey, I was asked this question. And the question was that, given this data set, come up with the factors impacting the outcome. Okay, most important was that factors should be very clear, that these are the factors that are impacting outcome. And so we take the more transparent model. Okay, perfect. All right, so we prefer the most transparent model out of all is decision tree, then the others, and the last one is the neural networks. Neural networks are least transparent model because we don't know exactly which parameter in the input is impacting the outcome the most. We know that given the input, it gives us the output, but we don't know exactly what exactly is impacting the outcome. So out of all kinds of models, neural networks are probably the least transparent models. Okay, neural networks are like people that, specifically those people who just give the answer and you can't explain how. Like, for example, it's a bad example I'm taking. The mathematicians from India, what was his name? Ramanujan, right? So Ramanujan will just say that, okay, this is the answer. And he wouldn't explain, or he would say that, hey, I can't really explain it. It just came to me. Okay, by in the dream or elsewhere, the outcome just came to me. So neural networks mostly are like that. Okay, and therefore, based on the problem statement, you generally choose the algorithms there. All right. So yes, that's a wonderful question. Now, great. But so far what I've done is I've answered your questions with respect to the looking at the bigger picture. So here, here's a quick checklist. Okay, you don't have to memorize this checklist. Okay, you don't have to memorize this checklist. All you have to do is just know the reasoning why something is there. Okay, and that you will come up with when you just cut down on all kinds of steps and try to just greedily try to reach out to outcome. That here's my data, give me the results. So you just take the data, split it, feed it to algorithm, and compare the results on the testing. Now, when you do this, then you'll have lots of questions saying, hey, why we are not having, what can I do further to improve it? Or why are we getting this error? In the previous one, the one that we just did, one thing that we had skipped, and two steps that we had skipped, one of them was visualization, and other was converting the categories into the converting categories into the numbers, right? Also dropping the columns and so on. So when you you basically just take the data, split it, feed it to algorithms, one algorithm, try to compare the results with the testing data, and then you see what errors are we getting. All the errors, when we debug, then we realize that it contains textual data, it contains the completely useless data, and so on. And therefore, it won't work out. So we'll go back and start cleaning the data. And once we are in good shape, then we move ahead. And then finally, we get the results. And then we get the results. We see that, okay, there's a lot of error. It's not good accuracy the model is giving. So we go back and then incorporate the remaining steps. And we keep on iterating over it so that finally we get great models. Perfect, great question. So let's just go with end-to-end project very quickly. We look at the bigger picture. What is it that we are trying to achieve? This is the first question. If somebody is, let's say, when you go for an interview and they just say that, can you do the label prediction or outcome prediction? You further dig deep into the question. You ask questions like, hey, how is it being done right now? Second, without the machines, how is it being done? That's the first thing. Second, you ask is, where this model is going to be deployed, as well as how we want to get the fresh data or get the new data. And when we basically do these question answers, then we get our thought clarity very, very, we get our thought clarity. So first is look at the big picture. Then we get the data, we explore the data for insights, and then we prepare the data for machine learning algorithms, okay? And then we prepare the data for machine learning algorithms, like in the sense that in case the values are missing, we fill it with something. We then realize that, okay, we heard that if we normalize the values, then we get better results because some of the algorithms are not really working well. And then we basically go back, normalize, or standardized. Then we explore different models, and then we choose one of the model, and then fine tune that particular model, and so on. Okay. Okay. And then once I have done the fine tuning, we present the solution. Once we have presented the solution to the team, then we can deploy, monitor, and maintain the system. Okay, any questions so far? Ajay, Amit, Ankit, Mukesh. Okay, great, great. I'm very happy that you found it useful. And I'm sure that this is basically something that is very useful. Okay, so I would suggest that try doing it in Azure ML. Try doing it without any steps. Okay, and when you try doing it, you'll get lots of errors, and then you go back and try to fix it. Okay, so we're going to, you can download the data from the Git repository we have displayed on the screen here. Okay, so a question from Ajay is that any outliers companies must consider. Okay, so before building a model, you are saying that from our data, should we drop the outliers? Is that your questions? Should that be one of the part in our machine learning pipeline? Okay, good question. Good question. So question is, before going ahead with our machine learning problem, should we drop the outliers? My suggestion is no, because most of these algorithms are okayish in handling the outlier, provided we have normalized the values. Specifically, when we are standardizing the values of a column, then that outlier will anyway be having either extremely negative value or extremely positive value, right? So most of the algorithms are kind of okay in dropping the outlier by itself. But yes, in order to improve the performance, that would be an extra step that you can go ahead with. But again, thumb rule remains that if dropping the outlier is improving the performance, only then you do that. Otherwise, don't do it. Okay? The thumb rule is, anything you do, if it's not improving performance or visibility into the data, then don't do it. Anything is improving the performance, then do it. If it's not improving, don't do it. All right, that's the perfect, the way to look at. Doesn't matter which algorithm you use. If let's say your purpose is not to come up with a transparent model, explainable model, or we can say there is a term called interpretable machine learning models, or interpretable AI is actually a branch of AI whereby we study the algorithms so that we can interpret their behaviors. Okay, moving ahead. So any questions at this point of time? Okay. My suggestion to all of you is the point that Ankit raised was a very, very important point, that if we are just cramming the whole process, we are just robotically copy pasting things, walking step by step, watching a video and doing it, that process would not help you understand what's going on, right? So I would say that try short circuiting it, try your own approach, just drag and drop things, try to see the outcome, and then compare the approach that we've taken and you're taking. Also, in a couple of problems like bike and others, you might have to look at more things later. So once, let's say, you're doing good performance, then you can go back. You can go back and study the problem a little bit more and see that, like, for example, one of the things that will come up is that what will you do if, let's say, there's an ID column? The quick answer is we'll just drop that ID column. The second question might come up that let's say we are trying to predict the bike demand. Let's say we are given the data about the bikes, okay? Like on this date, this time, when the climate was like this, and it was a working day, this was the result, right? These many bike demand was there in this geography. Question is, how will we come up with a model which can precisely predict the bike demand? You should try that out in Azure ML or anything. That's a very important problem posted by one of the bike companies. Okay, and so there, once you are done with the whole process that we have described, once you are there, what you have to do is, then in order to improve the performance, you again look at the problem and then see what can improve the performance further, specifically with respect to feature engineering. You might have to realize that, okay, we are given the time. So can we convert this time into, something meaningful? Because let's say time is given, say 0 to 24 hours, right? Now, if you notice, 0 as well as 24 both have exactly same behavior, right? 23.59 is same as 0, right? With 1 minute's difference. So the behavior of user is same in the two extremes, right? In case of bike, are you guys with me on this, or have I lost? Okay, let me go back. I think, thank you for reminding me. So one of the questions that, very, very popular question that comes like, okay, we build a very good model, but we are not getting a great accuracy on, say, bikes data set. Okay. Here is the bikes data set. Can you see my screen? So this data set has this column. Okay, it says that, what is this? Yeah, so purpose of this one is that given these other conditions, we have to predict the count. How many users, how many bikes went on that day. Okay, so first column is ID, right? First column is ID. And looking at this graph, you can see the distribution is kind of 1 each. Therefore, there's something wrong with this data. So probably this is an artificial data, right? Okay, now comes the hour of the day, 0 to 23, correct? This is the time, the bike was taken 0th hour, and we got, and on 0th hour of the day, on say a particular month, this is, I think, there is a count column. Okay. So is there a way to, I think I can just shift, yeah, using shift and scroll bar. Yes, so you can see that this is an artificial data, meaning it's most likely ID. Okay, most likely ID. Just like credit card numbers, when you compute it, when you draw it such that the y-axis contains the frequencies and x-axis contains the numbers, when it's equal, chances are that it's some kind of ID. Okay, now second is hour, right? Hour is the hour of the day, and then at this hour of the day we had how many bikes? You see, 47, right? We had 47 in this hour. But notice this, that whether it's 0 or 23, it's almost same, right? Because 23 is next day's night, correct? Next day's night. So whatever behavior user shows, like more demand in night or less demand on night, will be same for 0 and 24, correct? Amit? And yeah, everyone, are you with me so far? Perfect. So now in this case, what is going to happen is, it's a very important problem, okay? And it's a very, very, very common question that people ask in interview. First is about this, that what if we have an ID column in the data set? What to do? The answer is drop it. We don't need this data set. Question is, how would you figure out that this is an ID column? Just plot the the distribution of it using one of the techniques that we have explained. Then you will know that, okay, distribution is equal on every value, therefore it's not really going to help. Okay, it's not really going to help. The chances are that it's just an ID. Okay. The other thing that you should keep in mind, that in case you take all these values and the whole column is equal, if the whole column has only, say, false on everything, right? Then what you do is you again drop that column. Okay. I'm not sure if in this case it is there or not, but yes, that's another important activity. So here in this case, what we'll do is we'll break it down into 3, 4, 5 parts in a day, that morning, afternoon, evening, and night. Okay, we'll just break it down into that 4 or 5 parts and let that be a parameter. That will give you better results, because the algorithm will get confused that for 0 also I'm getting the same results, and for maximum also I'm getting the same results. Therefore, we need to break it down into 3 buckets, from 0 to this, from, let's say, from 2022 to, say, 7 a.m. we consider, or 5 a.m. we consider night. From, say, 5 a.m. to, say, 10 a.m. we consider early morning. 5 a.m. to, say, 8 a.m. we consider early morning. And from 8 to, say, 11 we consider rush hour, or 8 to 12 we consider the rush hour. And from 12 to, say, evening we consider that evening shift. Based on our understanding of the geography, we can break it down into those buckets. That'll be more helpful, because this will utterly confuse the algorithm that I'm getting the same results for minimum and for maximum. Okay, therefore there's something wrong with the parameter, therefore we need to change it. All right, perfect. I hope I was able to explain the question. The next question is from Ankit, is if there are 100 columns, probably not everyone would affect the final result. Do we simplify and reduce a few columns then, and then counter the argument in each column, maybe affecting a small amount? So we should not remove. Very good question. Anybody else wants to answer this question? It's a great question. And question is that good, good. So yes. So question suggestion from Ajay is that isn't this the same response to the outlier question? Correct. It's similar one that we should not drop the columns right away. But if you, there are multiple techniques to this. Okay, multiple techniques to this. Okay. One is that, first of all, we should not do too much of feature analysis upfront. That's a first thumb rule. Okay. You let it go and you basically let it be. Okay. And when you reach the entire pipeline and you see the error, then you go back and try to further take that mileage, like removal of outliers or dropping some of the columns and so on and so forth, right? So, but in few cases, we can actually take the call very quickly. One is like when we see a column called ID column, that is, say, unique to all the numbers and it has nothing to do with the outcome. In that case, that anyway gets dropped. That must be dropped, I would say. Second is with respect to the this very important question, that if all the values for holiday had the values for holiday been all false, is there a point of having this column? Is there a point of having holiday column? If all of these values are identical and false, do you think it would make sense to keep this column? Anybody? Okay, good, good. It would not affect it either ways. Yes, it would not affect, correct. So it won't have any impact. So I'll give you a very interesting example. Okay, in one of the research project that I did for one of the IITs in India. So what we had to do was, given the photo of something, we were supposed to predict some value. Okay, given the photo, we were supposed to predict this. And when I looked at the photos, each photo has, had like a huge frame around it. So it has a really big frame like this. Each photo has identical frame around it. So the values of these pixels, which became the features like this, was not changing across the instances, right? Because all of the images have identical pixels. So we decided to drop it. Okay. Now going back to Ankit's question. So one is doing it manually. Other is a very important point. Instead of doing it manually, what you do is you use another strategy called PCA. You will study in the construct chapter or challenge chapters as you go ahead. So PCA is one algorithm. What it does is it figures out that there is no variance or there's no change in a column, so we can drop those columns. Okay, instead of you trying to figure out, the algorithm figures it out. Okay, let's say here, imagine that only for one instance there was a difference in the dot. Okay, so we won't be able to drop in that case, but PCA will figure out that. Now, question from Ankit is that what's the point of dropping it explicitly, right? Now, the problem is that when you have too many columns, right? What's the purpose of dropping it? It sounds like we are deleting data. Isn't bigger data or more data more useful? Answer is no. More rows are better. More columns are painful. Okay? So the more columns you have, you require the more number of rows. Okay? When you have more columns, you should require more number of rows. In case your columns are reduced by way of deleting some parts, your algorithms perform better. Your algorithms or models perform better when you have less number of features. Yes. Okay, it's a wonderful discussion. I hope everybody is able to, is with me so far, right? So essentially, when the whole column's value are identical, instead of you manually deleting it, you leave it to PCA, and that answers the further question. A question from Mukesh: what if in future? What if in future the new data be loaded and suddenly the values are different there? A particular column has some value, right? In that case, in case we hard coded that drop this column, in case we did that, then we will be at loss, right? Therefore, we generally stitch something called PCA, and we tell PCA that all the columns that are utterly useless, as in that have zero variance, drop only those columns. Yeah. So in the pipeline, in these cases, if we have just too many columns, we stitch one more thing. We modify our workflow to include one more step, pre-processing step called PCA. PCA will basically drop some of the columns which have no change or no variance in the values at all. Good question. So question is, since we drop these features and when we want to do inference phase, like prediction phase, or you can say production phase, then you have to actually follow the same steps. You will have to drop all those columns that were dropped by PCA. Okay? Therefore, otherwise it'll throw an error saying, hey, your model was trained on this kind of data, but you're feeding me some other data. Therefore, it's wrong, and it'll throw an error. Okay? Therefore, the PCA needs to be done for both training and testing, as well as needs to be shipped to the production. Yes. A further question is, what happens in future if a column becomes invalid or it changes the meaning or purpose? Correct. In such cases, your model is becoming stale, right? First thing. So you have to retrain it. And when you are retraining it, the PCA will take care of it. Okay? Perfect. Perfect. So I hope I was able to answer your questions. This is a very important discussion, and I can assure you that if you are having a real project discussions, lots of things revolve around this. Okay. Also, keep in mind, I hope everybody is aware of what is underfitting and overfitting, right? So if you have more number of columns, the chance of overfitting is very high. Okay, if you have less number of columns, right, it is generally better to have a little lesser number of columns. Okay, if you have just imagine that all the values for the column are say 0 and only one value is 1, then you have like 100 such columns. Now what will happen is we don't get too much of learning from that column because we have only yes and no. Okay, imagine that out of say 1,000 times your mother asked you to have food, and you only said once out of those 1,000 times. No matter what was the dish, what was so every other column is changing, and so, or how should I say? Okay, let me put it this way. Let me put it this way. That imagine that imagine that there's a column called desert, right? There's a column called desert, and you were offered food 1,000,000 times. Okay, for all the except for one, all the 1,000,000 times, the desert was not served, and you did not like the food. Okay. And then suddenly, in one of the cases, the desert was served and you liked the food, right? Now, what will happen is it will be assumed, looking at the data, the model will learn that the desert column is the most important column, but it could be other columns that are impacting the outcome. Okay, it could be other columns that are impacting the outcome. So we'll kind of, the model kind of memorizes that if there is desert, that means it's yes, otherwise it's no. So it's a wrong learning. It's kind of a memorization or overfitting that happens when there are just too many columns and columns do not have significant variance. Our question is there a limit in terms of on how many columns or how much data should be included? Good question, but it's not quantifiable. It's not quantifiable. It has been observed when we drop these columns with very low variance, when there is no significant outcome, significant change in the particular column. If we drop them, generally models accuracy on test data is far better. Okay, training data model could perform really well in case there are too many columns, but testing data model performs far better if we have little lesser columns. Okay. Okay, a question from Ankit is it right to discuss? All right, it's a good question what Ajay asked. I forgot to mention that theoretically there is no way to figure out how many columns are good for this kind of data, but you can always figure out by the way of using algorithms. Some algorithms will take really long time, others will take less time, and so on. Okay. As a thumb rule, in case you need transparency, you use the decision trees or other models. In case you have very small number of records, in those cases, we use a model called SVM. Okay. A question from Ankit is it right to discuss this time how today's learning will be applicable in other ML scenarios like understanding what is in the image, say beach, cat, dog? Yes. Whatever we are learning right now is applicable to the holistic machine learning, right? Like in case of beach, or let's say in case of photos, the corner pixels are generally useless, okay? Generally useless. And therefore, or let's say when we were taking pictures, there was a particular point in the picture where there was a camera was defective and it was not taking those pixels. So that there will be a dark spot on all the pictures in that corner. So we can generally drop such features. And this is applicable in almost everything. All right. Okay, a question is, how is feature vector created in such scenarios of images auto tags? Auto tags as in, we need to tag by ourselves, the images are not given to us. No? Okay. A question from Ankit is that how is feature vector created in such scenarios of images, such as images auto tags? If I add a new image, system predicts what's in the image, like that, right? Okay. Okay. So actually, I'll actually describe that problem statement probably later. Okay. And yes, so generally the way when we are dealing with the feature vector, or when we are dealing with images and all, feature vector generally involves the pixels from the images, okay? And the only way we can reduce the features in case of such, the example you're taking, is by zooming the image, okay? By zooming the image, as in by resizing it to a smaller shape, okay? All right. So I'll come back to that. There's something called image embedding. I would love to describe it at later point of time. Okay. All right. So a question from Ankit is that, can you explain SVM and decision tree? Okay. For now, just understand this part, that SVM and decision trees are two algorithms that create their own models. Like we drew the line, similarly this one, these two, basically internals of it, we will discuss in the next chapter when we talk about underpinnings and constructs of machine learning, that how exactly these models work. But for now, it's important to understand that though we try all algorithms, but the thumb rule is, in case too few rows, use SVM. In case we need transparency, interpretation, interpretability, or we need transparency, interpretability, and what else? We need, let's say, transparency, interpretability, and or actually it's R. Okay, and explainability. There are multiple words to represent the same thing. Okay, so interpretable, explainable, or transparent models, you use decision tree. Okay, so I'll go into exactly how it functions probably at a later point of time. But for now, I think this much clarity is good enough. Okay. Also keep in mind that whether there are many models, actually the one that we study, SVM, decision trees, random forest, neural networks, and normal regression, okay, or logistic regression. Okay, so when it comes to normal predicting a value, we generally use the regressor, either linear regressor, okay, or In case we are doing classifier, then linear regression is called the logistic regression. Then SVM, recent tree. These are various kind of algorithms, okay, which prepare the models. Okay, we will go into more details exactly how these work in underpinnings and constructs. Perfect. All right. Okay, wonderful questions. So I hope this data set gives you more clarity. So this column is what? Anybody? Is it category or numerical? So I would recommend everybody to try this out, okay? To try this bikes model on Azure ML. Okay, so should we move ahead? So essentially, this is the discussion. You can download this housing CSV file, and these are the the steps. So we look at the bigger picture, frame the problem. Based on the problem statement, we select the performance measures, and then check the assumptions. Okay, frame the problem, and how do we want to use it, and which algorithm to select, and so on. Because here, when you are framing the problem, if let's say somebody is saying, no matter what you do, we want clarity on the decisions that you're taking, right? In that case, it becomes imperative that we would be focused more on the decision trees. Okay, now, so here in this case, it is basically whatever model we prepare is going to be used in as part of other software pipeline. Okay, so getting this right is critical. It affects the value. So we also check with what's the current solution and so on. So then we frame the problem. Okay, and then we understand whether it's unsupervised or supervised or reinforcement, and then whether it's classification or regression or it's something else. Now this available data, we basically, this is the purpose of the exercise that will feed data to algorithm and we'll get the training data model. And then we will also understand whether it's an online model or it's a batch model. Okay, so we got these answers. So in case of bike 1, where we have to predict the counts, is it a regression or classification? Anybody? In case of bike problem, is it classification or regression? You have to predict how many bikes went for given the climate, given the date, given the day, and so on. How many bikes were rented out? So this is regression. That's right. So it's basically regression, the bikes problem. Is it supervised, unsupervised, or reinforcement? Anybody? Supervised. Perfect. Supervised, and it's the regression. And we don't want to learn on the go, as in whenever the data is coming, we don't want to do the retraining. Therefore, it's a batch learning in case of bikes, correct? So we got these answers. Now we can move ahead with understanding the data in a little bit more. Okay, in this case, in the case of housing, the answer is same, like it's a supervised, it's a regression, it's a batch learning. Okay. Now, since it's a regression, what will be the performance measure? Yes? Yes, mean square error. What is mean square error? It'll predict some value, we'll compare it with the actual one, we'll subtract the two, the actual one and the predicted one, take the square of it and sum all such values over the test data set, all the rows, and then this is one row, this is another, like that, right? So predicted versus the actual label, okay? And this is the overall error. All right, so here we are showing that how to use the bootml to do it and get the data, download the data, and so on, and it will basically generate all of it. Okay. You don't have to really memorize all the steps. When you look at the problem here, okay, so one of the challenges people face is that here they go to kernel, and people basically have posted a kernel here. So they get confused as in what's going on here, okay? Is there a better data set? Bikes data set, okay, image bike. Yeah, this is bike sharing demand. Okay, I think this is the one that I was actually looking at. This is easy. This is a more clearer solution. So you can see number of total rentals, and season is spring, summer, and fall, whether it's a holiday or not, and so on. And date time, the hourly date, and timestamp. If you take a look at these existing solutions, the one that have been working really well, okay, so you can take a look at, let's say, this solution. It'll look really crazy to you, so don't worry about it, because this has come after lots of iterations. Okay, so you'll find that lots of things they're just doing it, creating more columns and so on. That hasn't come, you know, right away. What they've done is they have gone back and forth in order to, they have taken the inspiration from here and there, and they've tried all possibilities, and then they have come up with a model. So don't get, you know, depressed looking at these kernels. The idea should be that you will move forward, and these newer ideas like, okay, we can come up with new column, we can drop this column, that can be secondary. Okay, first important part is get to your error rate, and then go back and fine tune each part. Okay, there's a general strategy, and also you will get these clever ideas by looking at the data, by exploring data. And it's not really mandatory for you to, first of all, the first step is, let's just explore the data. It's completely okay to reach to the error stage and then come back and start exploring. Okay, and then the data quirks you can remove as a secondary part, though we have taken as the first one. These are something that you could do. But data cleaning you might have to do, because algorithms throw error if they observe null. Okay, feature scaling again is an optimization step. If you don't do it, probably your solution may not be greatly optimized, and so on. So we explore different models and so on. Okay, so this is where the cross-validation will happen. Okay, so original data set, we break it down into training, test. We don't touch it. We take the training one, break it down into two parts again, and keep on breaking it down over and over, right? And so on. Okay, and once we have our working model, then we can fine tune it, and then we can launch it. Okay. So hyperparameters are these characteristics or the decisions that you will take for a program. Like for example, number of iterations that we want to go for, or number of hidden layers in neural network, how many layers of neurons do we want to create, how many neurons per layer do we want to create. All of that is a hyperparameter. Okay, a number of clusters is again in a k-means clustering. So there are hyperparameters is basically kind of a way of controlling various algorithms. Okay. Now this is a very interesting point. Probably you noticed or not. This is an amazing chapter, amazing topic. We again address it in the constructs chapter, right? Next chapter. Here, what we are saying is that when we were doing our analysis, what if two algorithms have similar performance? Let's say we were doing this testing and we find that two algorithms, let's say random forest and neural network, both are giving equivalent outcome. So which one to keep, which one to drop? Okay, the answer is keep both. Train both the models if you have available CPU computing or GPU computing available. Train both the models. Okay, train both the models, and when needed, ask both of them the prediction. Okay, and pick the prediction which is getting the combined predictions better. Okay, it's like in a team you have multiple people, right? Multiple people, and whenever some situation arises, you ask multiple people that, hey, what does your understanding say? Should we go ahead or should we go back? And then based on the probabilistic answer, we go ahead or drop it. So we asked all the people that give me the probability that you think that we should go ahead. They'll say, okay, I think that 60% I'm suggesting that we should go ahead. The second one says that, hey, I'm suggesting that 75% probability of going ahead. So we do the average of two and see if it is more than 50% and go ahead. So that's like, combining multiple brains together to get the results. And you'll be surprised to know this is the only strategy that has been winning last 10 years. Combining multiple models is the only strategy that wins all the competitions on Kaggle or in building the real-time solution. Okay? And why so? Because every model has different way of looking at things. Like me and you, both are biased in some way, right? But when we are hiring somebody, you took an independent interview, I took an independent interview, and we predict the chance of hiring. If we combine the results of mine and yours, the chances are that our biases will cancel out. Okay, if you have, let's say, 10 different people interviewing somebody, the chances are that if they don't share the information between themselves, the chances are that all these 10 people will, when they give the result that, okay, my hiring chances are 60-40 and so on. So we can combine the results and get the outcome really well. This is called ensemble learning. Ensemble learning is kind of combined learning by using multiple algorithms, and that works every time. Okay, this is one of the reasons why we have diversity in the teams globally. Because when you have diverse team, like some are males, some are females, and some are colorblind, some are not colorblind, generally the outcome is far better. Okay, some are musicians, some are not musicians, some are, let's say, some are public speakers, some are not. So this way, if you have different people, generally as a team, the result is far better. Okay, so this is called ensemble learning. This is a great learning, and this is very much applicable to our normal life. Okay, a question from Ankit is, if results are similar, shouldn't we pick the one with more transfer? Not always, not always. If our objective is to just come up with best accuracy possible, right, then we ensemble these. And keep in mind that when we are ensembling, make sure that you don't do this, that, okay, we trained linear regression first, then again, we trained another linear regression, because both of them have identical results. If both of them are identical models, it is not going to give you any better results. Okay, you will be kind of, in real life, if you have your like 5 people which have identical thought process, they all are going to make you live in an echo chamber. Okay, because they all have identical thought process like yours. In that case, ensembling is not going to solve any problem. So the thumb rule is, when we ensemble multiple models, they should be diverse. Diverse in the terms of either the algorithm should be diverse, algorithm should be different, or algorithm should, if it's the same algorithm, it should be trained on different part of the data set. Okay. All right, so that's about this, and then we launch and monitor. Any questions with respect to it? Okay. All right, I think we should take a break for 10 minutes. Okay. So yes, these slides are available online. I'll just share the URL just in case if you are not able to access it. Okay. Okay, these are not shareable. I don't have the access to it. I'll share it. Okay. Is it not available in the my courses? Can you just check and let me know? We will try to make it shareable. All right, we will be, I'm taking a break for 10 minutes and back by 53 IST. Please post the time in your time zone. Hi everyone, are you back? So shall we start? Okay. Question from Mukesh is, can you please share the previous 2 sessions recordings as well? Sure, sure. Okay. All right. Okay, I'll just make a note of these. Things. What's the date today? Today is 8th June. Okay. All right. Sure, sure. I'll just check if the recordings are available or not. Okay, so let's move ahead. And do we have any questions around? All right. If you guys don't have any questions, so we can end it here. Otherwise, we can move ahead. Okay. So then we talk about here. Right. So then next one that we talk about is the classification. Same idea. Earlier we talked about regression. Then we talk about the classification. Okay. So in this project, we take a different example so that we get a perspective from both sides. Okay. And all right. So classification is basically classifying classifying objects into various labels or categories. The algorithm generates the model by getting the training. All right. And then once it's done, it can be used to. Okay. So we need to split the data set into training and test. And once that is done, then we do the rest. Okay. And and this dataset was another one that we had discussed earlier while talking about representing data. Thereby, basically here, there are total 9 categories and it is a classification task. Labels or categories is the same thing. And the input image basically is fed to the model and model classifies that image into one of the numbers. Okay, so basically, question is that when we have the data like this, how would we create the tabular form? It was answered earlier that we will basically convert it into numbers, and then we will basically stretch the whole picture into one dimension, and that'll become the, that will become our features. Then we feed this table into an algorithm and let it come with the model. And then once the model is there, we can predict whether 5, not 5. Okay. So one thing that you can simplify most of the problems. When you look at a particular problem, right now, let's say in case of MNIST, MNIST is handwriting recognition of digits. We have a huge data set which has handwritten digits along with the labels. Let's say we are trying to identify each one. So to begin with, we can do a simpler version of it. What we can do, we can break the problem into 5 and not 5. Let's say instead of predicting each digit, we are saying that we'll predict whether it's 5 or not 5, right? So that's the idea. And whether cat or not cat, and so on. So we'll build a 5 detector. Similarly, in case of cat not cat, which means we have converted the multi-class classification into binary classification. Okay, so and then we can use the kind of one-hot encoding to convert this into assign numbers to each of them, like 5 or not 5. You can say 0 or 1, and so on, right? And once we are done with creating a 5 detector, we can use the same strategy. All right. So now question is that since it's a classification, we can't use the mean square error because it doesn't make any sense. Because if we have to predict something like whether it's 5 or not 5 or cat or not cat in case of classification, the error we can't use, mean square error is what we can't use. Okay, so we use other methods. Okay, we use other methods, and the performance measures with respect to classifications are accuracy. Okay, and accuracy is basically how many work right divided by total instances, right? So that's about it. Now, the challenge with normal accuracy model is that it's little faulty. In case, let's say in the input model, there are 90 images that are other than 5, while 10 images that are of 5, right? So the accuracy is going to be how much? Okay, let's say there's this dumb classifier. What it does is for any image, it says that it's not 5 for this person as well as this person. So what's the accuracy of this model? Anybody? So we have a dumb model, very dumb model. What it does is when somebody shows it the image of any character, it always says it's not 5. Okay, it always says it's not 5. Now, what is the accuracy of this model? Imagine that there are 90 out of 100 total images, 90 images in the input were actually labeled as 5, other than 5, while 10 were labeled as 5. What is the accuracy? So it's able to predict that it's able to predict these 90 images correctly, right? Because it's not 5, right? These ones it's able to predict correctly. So the accuracy is 90%. So even though this classifier is like really dumb, because it's saying for anything without even looking at the image, it's saying it's not 5. So it's actually like correct 90% of time. It's like saying that even a stopped clock shows right time at least twice a day, right? Similarly, even a dumb classifier is right 90% of the time. Do you see that? Any questions around it? Have you guys gone through this? No, not yet. The classification? If you have any questions around classification, you can ask. Okay, so the accuracy is 90% in this case, which is horrible because it was supposed to be, it should be 0%, as it was suggesting. It should be 0%, but by the way of accuracy, that how many it's able to predict correctly, divide by total, that seems to be, little buggy. Therefore, we can't really use accuracy as the measure in many cases. So we learn similarly the case with cancer, whether it's right or wrong, predict the, in case it is predicting bad in every case, that there is no cancer. There is no cancer. Since there are 95% people with no cancer, therefore the accuracy is going to be 95% in case of if there's a model which is predicting no cancer. right? So this is a little crazy part about accuracy. So people generally use the one thing that you had, okay, this again a very good interview question. Okay, it's a very good interview question. People ask you when they're hiring you, they ask you a question like that: your friend came to you claiming that his model is like 99% accurate. What do you do in such cases? Do you just trust him, or do you ask him further questions? If you ask further questions, what would those questions be? Your friend comes to you and says that, hey, my model is giving 99.5 accuracy. What will be your questions? An answer from Ankit is the result of those 95% same? Is the 5% result data featuring in 95%? Yes. Good, good. So first thing you will check is that what is the balance of the labels, right? You will see that actually in the data, how many people have cancer and how many don't. Yes, so you will know clearly that, okay, so this one has this much percentage of label and so on. Therefore, this model is not really doing good. So you will see the label imbalance. That's the first thing you will do, okay? The other thing you will do is you will ask the questions like, hey, is it performing great on the training set or testing set? If he says training set, that means the chances are the model is also memorizing things and is overfitting, right? So this is the question that it has 99% accuracy, and the questions that you will ask is that how many percent is males and how many percent is females. Okay. Perfect. So now the much better way of looking at the performance is by the way of confusion matrix. So what you do is you lay out the predicted versus actual. Okay, predicted versus actual. The predicted, let's say the predicted is yes, predicted is no, actual is yes, and actually no. Meaning 62 cases, in 620 cases, it predicted correctly. Okay, predicted and actual are both yes. Predicted and actual both are no in this case. So total correct cases are how many? This, and this added. Right? So if you add these two, and if you add these two, right? So that should be, so these two are wrong, these two are right. This is called confusion table. This is called confusion table. It's actually quite confusing. So it's called confusion table, not confusing table, confusion table, because it shows which are the truth and which are the false. We can say confusion matrix. So we prepare in every case, we prepare the confusion table. In case there are more labels, right? So there will be more columns this side and there will be more columns this side. Okay, so in case of MNIST, how many columns are going to be there? It's going to have 10 columns, 0, 1 to 10, and it's going to have 10 columns this side, right? Okay. All right. So a question from Ankit is, in CAT's questions or male female question, how do you check the new data with the trained data? Is it matching each pixel or some other model? It's similar to my question earlier. Okay, so do you mean to say that what does algorithm do? How does it come up with the model, right? Is it going to match each pixel? No. See, one way could be that this is not model-based learning. This is instance-based learning, what you're suggesting, that we have a list of images, right? We have, let's say, a list of images. This is one image of the cat. This is another image of the cat. And this is another. So, and this is marked as cat, not a cat, and cat, correct? Let's say this is your training data set, right? Now, when a new image comes, imagine that this is the approach, that when a new image comes, right? This is, let's say, a new image, okay? And what we do is we compare it against this, compare it against this, compare it against this, and check which one it is closer to, right? Is that your question? Or do you want to unmute and ask?
Yes,
Okay.
Sandeep. So basically, if you are checking this cat with the other cat or dog or whatever, so what is exactly being checked? And this is something that I currently work on. I work in the imaging sector, and
Yeah.
this I usually, and what answer I've always got is it's a feature vector describing uniquely what is in that image gets matched with another feature vector in all other images. And that's where we know how similar is this image to the other image. So I'm just asking, what is is
Okay.
this feature vector or anything, how to
Okay.
compare?
Okay. So I'll be very, very, very upfront on this. This is not how we do it. Okay. This is not how we do. This is not machine learning. When we are doing this part, this is not machine learning because it's an instance-based learning. What's happening is we're comparing with each of them, right? Instead, probably I'll come back to exact problem that you're talking about, like face embeddings and other things. That's called feature vector. We'll talk about that later. Okay, so I'll come back to that, and here is the deal. So the model that we are trying to predict right now, instead of doing this way, what we're going to do, let's just go back a couple of steps. So first of all, we are going to feed this data set to our algorithm, okay? And this algorithm is going to come up with some kind of mental model of things, okay? Some kind of mental model of things. So in which, when you give the new image, when you give this new image to it, it will say cat or not a cat. Okay, so basically this is a very important part. Now, when you are taking this image, okay, and going to each of these and comparing against each of this, what's happening is that every time you have to do how many comparisons. If there are, say, 10 labels or 20 labels or 50 labels, you'll have to take each pixel, compare it, and that's going to be disastrous. So in the case of machine learning, we don't follow this approach. Now, the problem that you're talking about is twofold. I'll talk about that in a minute. Is everybody clear on this? Yeah. So traditionally what we're doing is we take an image, compare against all, and then say that, okay, this one is more closer to this, and therefore outcome is this. And how do we compare two images? I used to compare earlier. We take two images, compare this pixel against this pixel, subtract these two, okay? And then let's say this is V1. Then we take another pixel, and compare this. This is say V2. And after doing all of this, what we do is V1 square plus V2 square plus V3 square, like that. We'll sum up all the errors, differences in pixels. That's how we used to do without the machine learning. Now, I hope this approach is very clear to you. No. Instead of doing this way, what we do is we feed this telling that, hey, algorithm, this is the image and this is the label. This is the image, this is the label. An algorithm learns from it and puts his mental model in this file. Okay, we're going to talk about what does it mean by algorithm, what does it mean by this file, the model. This is called model. Okay, and this is the algorithm. Using model, then we can do the prediction. It doesn't have to compare against all of this, right? Amit, Ajay, Ankit, and Mukesh, we are all on the same page, right? Okay. Okay. Now, coming back to Ankit's problem, okay? I'll take a very simple example, okay? I think that will help all of you. That's something really trending, and I want all of you to get the feel of it, okay? Okay, so let me see if I can explain without any other things. Okay, now what people did was that they came up with some neural network. What it does is it takes the image, okay, and convert that into a list of numbers. Okay, what it does is given a person's photo, it will convert it into a list of numbers. Now, this is a model. This is a machine learning model. What it does is it's already trained model. Okay, it's already a pre-trained model. We generally call it FaceNet. Okay, I think I'll just take a digression. Okay, I hope that's okay with you. I'll just try to pick up another set of slides so that you get clarity on what I'm talking about. Okay, so what is that? Computer vision. Okay, so let me just walk you through okay. So it's a big digression, don't worry. It's something that anyway we'll have this in the class, okay? Let me just move ahead. It's just too many slides. So this is from my talk at Amazon. Those who are from Amazon, they would be knowing the seller platform. Okay. All right. Okay. All right, so some of the systems, so neural network, the model that they built was like this, okay? We gave an objective to the algorithm, the model, we gave an objective to the algorithm that, hey, these are the 50 images of the same person. Come up with these 20 numbers, okay? Come up with the 128 numbers or 20 numbers such that different persons should have these numbers really different, and same people should have these numbers very closer. We took the, imagine this for a moment, that we have the pictures of one person, like 50, say 120 pictures, and then we have the pictures of different people across the globe, hundreds of those, and they're labeled. They're labeled. Now, it's the same person and so on. Now, the problem that is twisted for now. Okay. Now, this is something we call. So what researchers did was they trained the model such that if we feed the same image, a person's same image at different time points, it should give the error as very small. This one, error in this one, very small. And if you feed the different person's image, then this error should be very high. Okay? And by virtue of that, the system came up with these numbers, saying that, hey, if we represent each face with these numbers, then it will basically suffice. Instead of picking up each pixel and so on, it's going to kind of come up with these numbers. And it's quite mysterious how that conversion happens. It's quite mysterious. It's done by neural network. And I'll go into more details on how it came into play. Right now, I'm just taking a very simplistic way of defining it. So when we are defining that, okay, how many numbers do you need to define the moving car? Right? Anybody? When we are driving a car, a moving car, its velocity and direction, how many numbers do you need? How many numbers, anybody? If we are driving a car, if you have to come up with the speed and the direction, so how many numbers would you need? Anyone? Let's say this is something that is moving on the ground. How many numbers do you need to define its speed and direction? 2, right? The speed on x-axis and y-axis, right? You can think of it this way, that let's say this is Earth, rectangular one, and this is the car going into this direction. This is east, and this is north. I'm taking a little bit more digression, don't worry. It's going to be useful to all of you, right? So you need how many numbers? You have 2 numbers. One is velocity in x-axis and velocity in y-axis, correct? These 2 numbers, right? This can be negative or positive. So it could be like this. It could be like this, right? So when we are representing a moving car, we can represent it by 2 numbers. Now, let's take a little bit a different example. What if we had to, let's say this is 3D, and there is a rocket going into the space. The rocket going into the space. If this is a 3D, how many numbers do we require? Anyone? To describe the direction and speed of the rocket? How many numbers? Anyone? 3, correct? The shadow, you can say the shadow on the x-axis, shadow on the y-axis, and shadow on z-axis. In the component in x-axis, y-axis, z-axis. Is everybody okay? Ajay, Amit, Ankit, and Mukesh. All right. So when as so you notice this that as the things become more and more complex, we need more and more numbers to describe though that thing, its behavior, right? Similarly, if we had a video, we will have time components. So we will have X, Y, and Z, and then we'll have time also. So we got four things, four characteristics to describe something that is moving, that at time t equals 0, its coordinates were at xyz, then at time equals t1, its coordinates were like that, right? And let's say along with the time, its temperature is also changing. So we will have the fourth column called temperature, right? So as and when the things become more and more complex, we need more and more numbers to describe them, right? Now, there could be a billion people on the planet Earth, or there could be more than that. So people came up with this 128 numbers. And these are called pre-trained models. What they do is you feed an image and it gives you these numbers. Question is, on what basis? People generally don't know this, don't know that on what basis it takes out, but some people have come up with many hypotheses around it. Okay, after training neural networks, like this is same, this is different, this is same, this is different, neural network came up with these out model such that people with the same face should have same result. People with different face should have different results, right? So that's called face embedding. Now the face embedding is so powerful that what you do is take the face, give it to the model. This model is a pre-trained model. I think it's trained by Google or a couple of more people on many images. So this, you feed it to the model, this is the input, the model gives you the output. So this is the output of the model. We call that the face embeddings, or sometimes we refer to it as a feature vector. Generally, people have noticed that this is generally representing things like the eye size, these 4 points in the eye, and so on. So it doesn't really have a connotation. It's just hypothesis that these numbers might represent nose, mouth, this and that. But people don't have a clue on how to, even the build makers of it don't have a clue that what does each number represent. Okay, these numbers are a result of a neural network. That neural network has been trained on is, in case the images of the same person, give out the similar numbers. If it's a different person, then give out this. Okay, now are you all with me? This is called face embedding. Same thing has been done for word embedding, whereby each word gets converted to the word embedding. You'll be amazed to know that whether face embedding or word embedding, if same thing is passed, then the difference between this and that is almost zero. Like, for example, as an experiment, you guys can also do it. I'll upload this data. So what I did was, and the face embedding, the whole thing is installed on CloudX Lab if you want to try it out. So what I did was, I downloaded top 1,000 actors around the world, actors and actresses, okay, from IMDb, their images I downloaded. And what I wanted was that I wanted to find out which person, which actor do I look like. So what I did was I computed my feature vector of my embedding, and I computed the embedding of each one of these. Is it clear to all? Ajay, Amit, Ankit, Mukesh? Okay, so I did this 1,000 times calculation. I got these 1,000 set of 128 numbers. So once I was done with that, all I did was I compared each value, like 0.2 with 0.3, 0.1 to this, 0.3 to this, and so on, like that. I compared with all of them. Okay, and what I did was, after subtracting this from this, I squared it. After subtracting this from this, I squared it, and so on. We computed the mean square error, and then summed up all the value. And then I did not really I basically compared I computed the mean square error between my numbers and their numbers, right? Because if I compare pixel by pixel, the result will be very aberrant. Okay, why? Because this face net understands the face. It knows that one person has this characteristics. So it has figured out, like, distance between eyes are one thing. The shape of eye is different. It knows that specks need to be avoided. It knows that beard need to be avoided. It knows that the hairstyle need to be avoided. Okay. Also, a little bit of wrinkles here and there need to be avoided. So this face net understands that. Okay, and ignores those features, those characteristics in the image, and comes up with these numbers. And then what I did was, I compared against all of them. I found that the distance between me and this guy was the smallest. So you can see I actually looked very much like this guy in younger times. Okay, so you can see that it is kind of maybe matching the nose shape. It's kind of matching this part. You see that, and so on. Okay, so this is the outcome of word embedding. Is everybody clear what I did? So though I did not do any machine learning per se, but we could have done the machine learning. What we could have done is, we could have converted face into this. Let's say, in my case, let's say one of the projects that I'm about to launch is that in a co-working, there are hundreds of people who come every day. And based on their photo, I want to open the door. So how would I do it? How would I do it? Okay, how would I do it? I would basically take their photos, everybody's photos, convert them into numbers, right? Now on one hand, so what I'll have is, let's say this is the table. Sorry. Okay, this is the table, right? And this is the labels. Okay, and let's say I put the name against each of them. Like that. Okay, and what I can do is, I can basically, in case of this guy, I'm not going to really, I'm going to actually do this way generally, the way I described. Okay, the way I described, that whenever somebody is coming, I'll just go through this list and compare his numbers against each of their numbers, and predict which one this person is closer to, the one who is entering, showing the card, and then quickly give the answer that, hey, this person's name is such and such, and he should be allowed. Okay, he should be allowed. And all, of course, while subtracting, I'll also keep a minimum threshold. If the error is bigger than this, that means the person is not registered with us. All right, that is one approach. The other approach I could take was this. Okay, other approach I could take was this, that we convert every face into 128 columns. This is 128 features, right? This is 128 features. It'll have like many columns, and against each one of them, I mark that, I mark the person's name. Let's say label. Okay, and then I'll train it on SVM. These are the features, and this is the label. I'll train it on SVM because it has less number of rows. I don't have like thousands of photos of everyone. Therefore, I'll just use SVM to do the training. Then we'll get the model, and whenever somebody is entering the building, we will let it predict whether the name of the person. Okay. So that's the idea. That's the idea. And but in most of the cases, actually, the machine learning this way doesn't work. The better way is just use this technique whereby compare it against each of them and then come up with the result. Okay. I hope this was useful to all. Yes? Okay. A question further from Ankit, just checking the same concept of cat would be, we would take out the unique 28 number for new image, match it with neural networks trained data. Good question. So here, a very, very important part. So here, why we were able to do this, why I was able to achieve this. I was able to achieve this because I had a face net. I had a face net which could convert a face, a photo of a person, into these numbers. That's the important part. So using FaceNet is a pre-trained neural network. The model is this. It has the understanding of the face, and it gives out this. Now, let's take a case of cat and not cat. If we don't have a pre-trained model for the cat, it may not work because FaceNet is trained for finding similarities between the faces. Okay, so you have this FaceNet cannot work for object detection. And what we're talking about in our case is the raw model, right? We're saying that we have no pre-trained model. We have to do everything from the beginning. Okay. All right. So that was one discussion. All right. Then we talk about the confusion table, confusion matrix. Using confusion matrix, we basically come up with precision and recall. And once we have, like, there are multiple parts to it. This one is called true negative because it is truth and negative. Okay. And then we have false positive, and then we have right. So this is called false positive. This is called false negative, and this is called the true positive. So true positive, true are the ones that have resulted correctly. False positive and false negative are these which are wrong answers. All right. So based on the true negative and true positive, we can calculate the precision. Precision is calculated like this. Okay. So you can see that. Okay, so there are two things. One is called precision and recall. Precision means how minimum erroneous it is. Recall means how much it can recall. So precision and recall are opposite of each other. Somebody, let's say there is a person who calls everybody a thief. The recall rate could be 100% of thief. If there is a person who basically calls very selected people as thief, the chances of it missing out on some of the thieves is higher. So a precision one may not have a great recall. Okay, so that's about precision and recall. Have you guys went through this discussion? Not yet, Ankit? And others? Okay. Ajay? Amit? Mukesh? Okay. Do you have any questions for me? I'll come back to your question, Ajay, in a minute. Okay. All right. So, question from Ajay is, sorry to ask a stupid question. This is not a stupid question. It's only the way we look at it. Okay. Taking a clue from Mission Impossible movie, how ML can prevent from falsifying the facial features, such as using a good question. Good question. So, probably what we have to do is gather more data about that these facial features are false, these facial features are real, and we train it. And you'll be amazed to know that this is exactly somebody did recently. So what they did was they created two neural networks. One was falsifying the faces, other was detecting the faces. Okay, and that magic is the one that got the Nobel Prize. Okay, so and right, there's the magic that came up with the face embedding. That's the model that actually came up with the face embedding. Okay, so yes, so if you have humongous data, or let's say you build a model which knows how to, which learns how to create face, how can it does that? Take the random image, does some kind of machine learning on it, and create output which has a image. So if a machine learning model can basically what Yoshua Bengio did was that he took two models. One was falsifying the facial expressions, other was predicting that this is a false image, this is a real. And that magic is just amazing. I'll just show you. Okay, so that magic is just so amazing that so it's so amazing that it's you will find it very, very captivating. Oh, sorry. You see that? I'm going to skip to a little ahead. So the program has learned how to create faces. You see that? All of these faces are negative, as in false faces. And what it's doing is that these faces, it's mixing with the new ones. Okay, see that? This faces, it's mixing with this particular face. And new faces are being generated. You see that? So it's mixing this with this, you're getting this with this, getting this with this. Okay, so this is just amazing part. All right. So yes, it's not the entirely hypothetical question. It's actually a very relevant question. Probably Yoshua Bengio must have thought about the same thing for falsifying the face expression from Mission Impossible, and he ended up there. All right, great questions. See you, Ajay. I think he needs to drop. And that's right. A question from Ankit is just checking the same concept. I think this one I have answered, I hope. Okay. All right. Ankit was able to answer the questions, this particular question. I'll just paste it in the notepad. This question. Okay. Okay. So yeah. So basically, in the discussion we have is we're not going to go with the FaceNet. FaceNet is basically if we have a trained model which can come up with the characteristics of cat and dog, then what you're saying is correct. Then we don't need to train any model as such. We can just use it out of the box. Okay. So, but in reality, if the problem is faced to me, that that come up with the model which is predicting male or female, probably I'll just use the face embedding. Okay, instead of starting from the beginning, I'll basically do is for every face in the training set, I'll convert it into face embedding. That'll become my features, and the label like cat or dog or like male or female will become my labels, and I'll feed it to any of the neural network model, and then I'll let it predict. But if I don't have the embedding data, if nobody has the pre-trained model, then probably I'll train it from the beginning. All right, so great. And a question from Ankit is, all tech companies have trained model to identify which image is there, right? I believe it would be the same concept, even if the neural maybe something different, if not face. Yes, correct, that's right. So you are right. Okay. All right. So, okay. Yeah, this one, right? Perfect. Moving ahead. So, yes. Great question. So that's the discussion about now. So we talked about this part. All right. So if you don't have questions, so you can move ahead. So we talk about recall and precision. So in general, precision means the one who makes least amount of mistakes. Okay. It's okay for if a model is having high precision, that means that it's okay for it to leave few of the things from being identified, but it would not identify a wrong thing, right? So precision is, somebody who types really slow, but does not use backspace, okay? So that's precision. Now the other guy called recall, it types really fast, but it keeps on deleting all the time. So precision and recall are two different criteria. Sometimes you use precision, sometimes you use recall. And in case you need both, you will use F1 score, which is a combination of these two formulas. Okay, so I would suggest that you take a look at this discussion in more detail. That will help you understand the precision and the recall. Okay, so if baby safe videos, if you want to tag and we don't want to take a risk, then we optimize our model for precision. And in case we are otherwise, let's say our objective is that let's say we are catching somebody from stealing things, and in that case, from a supermarket, in that case we'll prefer the recall, right? So this is a very, very, very important discussion. Please go through this one. Why I talk about it is that there is a common question that people ask, that how can we trust a machine? How can we trust a machine? So to answer that question, you have to explain that what it is mean by training set and testing set. What does it mean by cross-validation stuff? And then you also have to tell that the kind of mistake your model makes. Is your model trained on precision, or is your model trained on recall? Okay, so this is a very, very important discussion. So I would suggest that you go through this discussion, and if you have any questions, you can again ask in the next session. And here, it's not an empty discussion because it's an end-to-end project also. So make sure that you go through it, and then all of these are described in more details. Okay, if you have any questions on this, please let me know. Okay, so basically here all we're trying to show is that as we fine-tune the model, if we try to improve the recall, the precision will drop. If we try to improve the recall, if we try to improve the precision, recall will drop. Okay, so we need to come up with a position where, based on our problem statement, let's say we don't want to take a risk at all when we are showing something to the people. Okay, we don't want to take a risk. in that case, right, if you want to, you know, if you don't want to take a risk at all, then we tune our model to high precision. In that case, it'll basically let go of few edge cases that look like same thing and so on. So go through this discussion that will help you the precision versus recall. And the next thing is ROC curve. ROC curve is for the ROC curve is for identifying how well our model is doing. Okay, and for that we have defined some of the metrics. Okay, to compare the models, people generally use ROC curve. To compare the results of our model, people use the precision or recall as the metrics. Okay, so just go through this discussion. So we learned about confusion metrics, precision, and recall, and then the trade-off between the two and the ROC curve. Okay, so then what we can do is, once we have figured out a binary classification, 5 versus not 5, then we can assemble those and either do 1 versus all or 1 versus 1 for multi-class classification. All right, so that's what we've discussed here. Please go through this discussion so that we can have more detailed in the next session. All right, so that's about the two. If you have any questions, you let me know now. Okay, so this is multi-class classification, whereby there are too many labels. Here there are 10 labels, and we are doing that. Now, multi-label classification is little different. Multi-label classification is that given a photo, in a photo there could be multiple things, right? Like, for example, here, given a movie, we have multiple labels. That it's a biography, it's a drama, it's a sport. Okay, and also I'll just show you this nice photo. Yeah, you see this? Okay, this is a camera that I built. You see this? In this photo, you have a person, you have a bike, and you have a person on the bike, right? So essentially, this is called the multi-label. In this photo, we have a car, we have another car, and so on. So this is called the multiple labels. Okay. Similarly, let's say in a sound clip, you need to identify that. This is called, basically, such kind of cases are called multiple labels. Okay, so what you do is we basically create the labels as set of columns. Instead of one column, there will be multiple columns, and each column will represent one of the labels, and then you can mark a tick tag or not. Okay, so please go through this and also make sure that you are able to do it using HRML as well as BootML. Okay, if you have any questions, just let me know. We will have the session next Saturday at the same time. Please feel free to drop in. And in the next session, what we are going to do is we're going to let me just exit this. Okay, we're going to continue very important topic called underpinning. Underpinning is a very, very important topic, and I would strongly recommend that be ready for the underpinning chapter. All right, so I look forward to see you in the next session at the same time. If you have any questions even related to the topics that we discussed today, the regression and the classification end-to-end project, let's discuss it in the underpinning of ML. All right, so I totally enjoyed your questions. Feel free to ask these questions. These questions are very important. I hope I was able to answer your questions. Thank you, Amit. Thank you, Ankit. Thank you, Mukesh. It's good to have 3 people in the class, because this gives a more bandwidth for questions. Nevertheless, trust me, most of the time, all of us have similar kind of questions, and all these questions are extremely important. So do not hesitate in reaching out at any point of time, because in case you do not ask questions, or you think that your questions are not smart enough, the chances are that you will lose interest in the topic, while this topic that we are learning right now is the most important topic that the human species need to learn. Okay, personally, I believe this part. All right. So great. I look forward to see you next Saturday at the same time. Thank you, Amit. Thank you, Ankit. Thank you, Mukesh. It was great to have all of you. I'm very happy that you liked this session very much. Bye-bye. Have a good day.